So last day I have introduced concept of noise temperature and what is noise figure. So today we will study these parameters in details, and we will see what are the importance of these parameters when we go for any millimeter wave system design, and after that we will calculate the SNR for any given millimeter wave system. And as an example, I will show you one application example, a passive imaging millimeter wave system which is already in use, and finally I will be introducing some different popular architectures, transceiver architectures used at millimeter wave frequencies. So let's start with the noise, its concept, from where it comes and what is the effect at millimeter wave frequencies. So for any given system, noise level, it sets the lower limit on the strength of a signal that can be detected. So now, the sources of noise, it can be different. It can be thermal noise, short noise, flicker noise, plasma noise, quantum noise, etc. So among these, thermal noise, it plays the most important role, and its contribution is highest among all these different noise sources. So why thermal noise happens? This is due to random fluctuations of dielectric molecules, and inside metals also due to random motion of electrons due to thermal agitations. We also have short noise, typically in solid state devices and in tube based devices, due to random recombination of electron holes and random motion of charge carriers. Then we have flicker noise. This noise it varies inversely with frequency. At millimeter wave frequencies, the effect of flicker noise is negligibly small. Then we have plasma noise. Let's say we are sending some millimeter wave signal through ionosphere or some charged medium. So in that case, this charged medium, this charged particle, they will also vibrate due to thermal agitation, and due to that we have some contribution of noise. And then quantum noise, this is due to the quantized energy levels of charge carriers, but again contribution of quantum noise is negligibly small. So as I said that the contribution of thermal noise is highest among these. So mainly in this class we are going to concentrate on the effect of thermal noise. It's also known as Nyquist noise or Johnson noise, some other names. So now let's say we have a millimeter wave component. It can be an amplifier also. Now for any amplifier, the gain will be specified. You can consider not just millimeter wave amplifier, it can be a very basic common emitter amplifier. So in common emitter amplifier test, if you remember that what we did in our UG first year class, that the signal handling capacity of a C amplifier. So in that case, the amplification factor is given. Then what we do, we change the input power level and measure the corresponding output power. So this amplifier or any other two port device, we always assume it will work as a linear device. But what we see for C amplifier, if we keep on increasing the input power level, at some point it starts to deviate from that linear characteristics, and the output waveform, it is distorted. It's not an exact replica of the input waveform, and we call that it enters the nonlinear region. So if I plot then P out versus P in for the first part, it will be a straight line, and then it will deviate from the straight line. So if you look at this graph, you see the first part, it looks like a straight line. Here we are showing P out in dBm versus P in again in dBm. So if we keep on increasing the input power level, at some points the device it saturates. So it determines the highest input power that can be applied to this particular component, or it can be also any instrument. And again after that, if we keep on increasing the input power level, so at some point the component we might burn the component. So we call that point is the failure point. Now, if I go to lower power level, you see the lowest power level that can be sensed by this component, or if it is an instrument, by the instrument, it is given by the noise floor. So, this noise, it comes due to the various reasons we discussed earlier, and it is generated inside the components or instrument itself, and there would be some noise which is also coming from outside. So, we will discuss all these points and how to model this internal and external noise for any millimeter wave systems. So, last day we have seen that in general noise power from any resistor which is at a temperature T, it can be given by this expression 4 kTr Hf by kT divided by exponential Hf by kT minus 1. Now, if we consider a low frequency high temperature case, so that means Hf by kT much less than 1, this condition is also called Rayleigh-Jeans approximation. So, in that case e to the power x, we can terminate the exponential series by its first two terms. So, it is 1 plus x, that means 1 plus Hf by kT. So, we have finally then Nf equal to 4 kTr. So, this is the noise power available, the noise power generated by the resistor. The corresponding noise voltage RMS value is given by square root of this 4 kTr volt per hertz. We are not considering any bandwidth. So, if we consider the noise power over some given bandwidth B, then we have to introduce a bandwidth term here, and it will become square root of 4 kTr into B. Now, also we have seen last day that whatever power is being generated by this resistor, it is not available to system. You recall maximum power transfer theorem. So, maximum power that can be extracted from this resistor, so that is given by maximum power transfer theorem when load is matched to the source resistor, or if we connect another resistor of the same value R. And in that case, if we calculate the noise power that is being absorbed in that load second resistor, it becomes independent of resistor. So, the value is given by Na, which is of course a function of frequency. This is equal to k into T. K is the Boltzmann constant. So, important conclusion is that then available noise power is independent of resistor. And noise power we can also express in terms of some equivalent temperature, and in that case that equivalent noise temperature Te for a bandwidth B hertz, we can express T equal to Na by Kb. We have also seen that if a tank circuit, a LC resonator is connected to this noisy resistor, then the total noise power kT is divided into two parts, and half is stored in each inductor and capacitor. That also we proved. Next, we will discuss about the external noise sources. So, external noise sources, it can be many things. So, let us say we are using any wireless millimeter wave system. It can be also one radiometer. So, now you see external, we have sun, we have stars and galaxies, they are constantly illuminating Earth's surface. So, some of this power will be attenuated by atmosphere, and then it will be re-radiated by the atmosphere. We call it downwelling radiation from atmosphere, and by this downwelling radiation from atmosphere, Earth's surface is constantly being illuminated. So, if we point any antenna towards Earth, then all this re-radiated power from Earth's surface, it will be collected by antenna, and it will work as an external source of noise. We quantize this external reflection from Earth's surface by its brightness. I will introduce the parameter and we will discuss its effect in details later. We also may have some external sources, some other wireless link maybe, and we also have external let's say Bluetooth device, Wi-Fi device. So many wireless systems already are in use. It can be mobile base stations, it also radiates their harmonics, and it can be at millimeter wave frequencies. So there are many sources, but here mainly we are going to concentrate what is the effect of this downwelling radiation or brightness from the Earth's surface. So let's study brightness in details then. According to Planck's law, inside a closed cavity constitute of a black body of temperature T, the apparent intensity spectral density per unit solid angle incident on any point in the cavity, which can be given by watt per meter square steradian hertz, is given by brightness B. This is equal to twice h f cube by c square divided by that exponential function. Now, what is black body? For black body, it is called the perfect absorber or perfect emitter at the same time. So whatever it will absorb, the whole power it also will re-radiate. Or absorption coefficient is 1. Similarly, its emissivity, that is also 1. Now let us consider a closed surface. It's a made of black body, and inside it is radiating due to its temperature. And let's say what radiation is falling on a surface here of area, let's say A, we want to calculate. Now then radiation, it's coming from all different angle over this, and now we are defining one unit solid angle, and let's say we are calculating what is the radiation coming through this unit solid angle, and then we integrate it over the area, incident area A. So then the brightness, as you see, it represents the brightness if we consider it per unit area and per unit bandwidth, unit hertz. So you look at the unit of brightness, it is watt per meter square per steradian hertz. Now if I want to calculate the overall radiation received by this area A, in that case simply we have to integrate in external, we can say we have to integrate it B over the A d omega over all the available solid angle. So we can also use similar concept for any antenna. So let's go back here. So we are representing any earth surface, let's say here, and considering the radiation coming from an area AS, and this radiation now it's in arbitrary direction, and some part will impinge on the antenna. Antenna diameter is given by antenna area is given by AD, and this antenna, it makes an angle theta with the zenith of this earth surface AS. So obviously the power, scattered power or radiated power, whatever received by this antenna, it depends on this angle theta, it depends on the polarization of antenna, and also the surface roughness of this surface, and the dielectric constituents of this earth surface. So it depends on so many factors. Now let's say we are defining a parameter J, which represents the spectral radiant intensity. So watt per steradian hertz, then the angular power spectral density emitted by surface area AS in the direction theta. So what we have to do then, J, that is equal to L AS cos theta, where L, it is called the radiance. So we are considering radiance is simply the brightness per unit solid angle per unit area. So what we are doing here, then we have to multiply L by this area term to obtain the total radiation received by the antenna. So, for that we can't take simply AS, because the antenna it's making an angle theta. So, we are taking the projection of S and it becomes then AS cos theta. So, then the spectral radiant intensity at the antenna point, it is equal to L AS cos theta. So, this is for unit solid angle. Now, the antenna, it substitute an angle AD by R square. If we assume that R is much more than AD, then the solid angle substitute by the antenna, it is given by AD by R square. Then the total power impinging on antenna, which is N external. So, for that we have J per unit solid angle, we have to multiply it by the total solid angle given by the antenna. So, this is J AD by R square. Now, if we put the value of J, which is we have seen L AS cos theta. So, it becomes L AS AD cos theta by R square watt per hertz. So, this is the total power received by antenna from a surface area of AS due to its radiance L. Now, we can show that the brightness of the source as seen by antenna, it is nothing but L. How? We are just considering the opposite scenario. In this case, we see that the surface area AS, what solid angle it makes to antenna, and then we calculate the brightness for that. So, solid angle subtended by the source as viewed by antenna, this is then the area divided by R square, but we have to take the projection. So, it is AS cos theta by R square. Then the perceived intensity of the antenna or brightness perceived by the antenna B, this is equal to N external divided by AD divided by AS cos theta by R square. So, total power we know, intensity we know, and that we have to divide by the angle. So, that then it will have the value per unit solid angle. So, if I put the value of N external from previous equation, so B it becomes simply L. So, we see that whatever may be the angle, whatever may be the AS or AD, brightness perceived by antenna, it simply becomes L. Now, brightness, it depends on the surface roughness of earth, it also depends on the dielectric constituents of earth, and obviously it depends on frequency. Under sun, it will have some value, under cold sky at night it will have some different value. So, roughly if we consider low frequency case below 30 gigahertz and high temperature, B, this is twice kT f square by c square, and this is we are considering whatever power it is radiating, we can receive all of this. But if the antenna is linearly polarized, we can't receive all of this power, only we will be receiving half of this. So, in that case, for linearly polarized antenna, then B equal to kT f square by c, and the corresponding T, it obviously a function of frequency. So, approximately this is 2 into 10 to the power 14 by f under sunlight, and 10 into 10 to the power 9 by f whole squared under clear night sky. So, it varies with the condition. So, we have seen the effect of external sources, typically the radiation from earth surface. Now, let us consider the noise contribution of the components of any receiver chain, and from that let us calculate the overall signal to noise ratio for a given receiver. So, let us start with a simple 2-port network. So, whenever any power is incident on that 2-port network, let us say the incident power is PS, then at the output side we have the gain of the two port component multiplied by the input power, that will be the available output power. But at the same time we also have some noise with the incident power PS, and in addition to that noise the component itself will add some noise. So then the at output point, if we calculate signal to noise ratio, it will be lower than the signal to noise ratio at the input side. Why? Because the component is also adding some noise. So overall noise contribution, then it will increase at the output side. So let us first characterize one two port component simply when we are not considering any external noise. So after that we will add some external noise from left hand side, and we will calculate the noise overall noise contribution of the two port device. So let us start with a simple two port network. Let us say this two port network temperature, it is in thermal equilibrium and the physical temperature is given by Tphy, and the loss factor of this two port network is L. So if we want to represent in terms of gain, then simply L equal to 1 by G. Now this two port network itself, it will produce some noise. So in that means we can represent this two port network by an equivalent resistor at some equivalent temperature Te. It will give the equivalent noise temperature, and which we will place on left hand side of this two port network. So for the first case we have noise generated internally, and in the second case this noise we are representing by effective temperature Te followed by a noiseless two port network. So then in internal we can write down this is K into T. If I consider per unit hertz, then it is simply K into T. So this is KT physical minus KT physical divided by L, or we can write down this is KT physical into 1 minus 1 by L, where L it represents the loss ratio. So if I want to represent in terms of gain, then L will be simply 1 by G. Then the corresponding equivalent input noise temperature we want to calculate. So then corresponding noise temperature, if this is Te, in that case KTe, this is equal to L into N internal. If I look at this second network, so Te, it's now providing me the N internal. Then we have a noiseless two port network, but again its loss is given by L. So we can write down then Te, this is equal to T physical into L minus 1. So this is one important relationship. So if the physical temperature is given, let us say the physical temperature is 300 Kelvin. So then if I know the loss value, then we can calculate what should be the effective noise temperature Te. Let us take one example. Let us say we have an attenuator, 3 dB attenuator. It is matched attenuator at 290 Kelvin, and it is connected to a RF source. Then the Te that must be added to the source equivalent noise temperature is 288.5. So how we are getting? So 3 dB, this is we are considering power loss. So then in fraction we can write down how to calculate the value in fraction. So it will be then simply 10 to the power 0.3, and you put the value of L here, then Te, that is equal to T physical, which is 290 multiplied by L minus 1. So it is 0.995 and the value is 288.5 Kelvin. Okay, so now we will take a break. After that we will see, let us say we have also some external noise which is incident from left hand side on this 2 port component. Okay, thank you.